In this lab, we will look at the causal discovery using a Bayesian network. So in step 1, we imported the data and we explored the data and we carried out some pre-processing on the data. And in step 2, we measured causal inference using propensity score matching. And in this step 3, we will carry out causal discovery using a Bayesian network. Propensity score matching is a valuable tool for causal inference, but it comes with several limitations that researchers should be aware of. Assumption of unconfoundedness. Propensity score matching assumes that all confounding variables are observed and included in the model. If there are unobserved confounders, the estimates may be biased. Correct model specification. The quality of propensity score matching depends on correctly specifying the model for the propensity score matching. If the model is misspecified, it can lead to biased estimates. Overlap assumption. Propensity score matching assumes that there is overlap in the propensity scores between the treatment and control groups. If there are regions of no common support, matching becomes difficult. Large number of covariates. When dealing with a large number of covariates, achieving balance on all of them through matching can be challenging. Sensitivity to propensity score model. The choice of the model used to estimate the propensity scores can impact the results. Different models can yield different estimates. Loss of data. Matching can result in a loss of data if some units cannot be matched. This can reduce the effective sample size and statistical power. Inefficiency. In some cases, matching can be inefficient because it discards potentially useful information in the unmatched units. Difficulty with multivalued treatments. Propensity score matching is more straightforward for binary treatments. When dealing with multiple treatment levels, the propensity score may not be as informative. Difficulty with time-varying treatments. Propensity score matching is primarily designed for static treatments. When treatments change over time, additional methods may be needed. Difficulty in handling missing data. Propensity score matching assumes that all covariates needed for matching are observed. Handling missing data can be challenging. Inability to address selection bias. Inability to address selection bias. Propensity score matching can only balance observed covariates. It cannot address selection bias due to unobserved variables. Lack of generalizability. Propensity score matching results may not generalize well to populations or settings that are different from the one in which the study was conducted. One of the largest challenges with propensity score matching is the fact that we have to decide what would be the treatment variable in the dataset. In this step, we will perform causal discovery to find treatment variables and confounders from the dataset. Causal discovery. Bayesian networks, BNs in short, can be used for causal discovery from observational data. In fact, they are one of the primary tools for this task. A Bayesian network is a directed acyclic graph, DAG, that represents the joint probability distribution over a set of variables. Each node in the graph corresponds to a variable, and the edges between the nodes represent probabilistic dependencies between the variables. causal discovery is primarily concerned with the first phase of Bayesian network modeling, which is learning the structure or the graphical representation. The learned graph from this phase often represents a causal structure, where the nodes represent variables and the edges represent causal relationships. The structural learning process is able to identify these relationships and the direction of influence based on the patterns and dependencies in the data, which makes it a powerful tool for causal discovery. However, it's important to note that while this structure can suggest causal relationships, it does not definitely prove them. There might be hidden or latent variables not included in the data that can influence the relationships. Therefore, any causal conclusions should be drawn cautiously and ideally should be supported by domain knowledge or further experimentation. First, let's try HillClimbingSearch to develop the DAG. And DAG is directed acyclic graph. So let's look at DF. DF gives the country and the region, country income, and all the other attributes. There are 120,680 data rows and 61 data columns. Let's subset the data the data rows belonging to the country New Zealand. Let df nz equal df square bracket df country dot country equal New Zealand dot copy opening close bracket. Let's print the df New Zealand. So df New Zealand is all the subset of the df data frame for all the country equal to New Zealand, for all the data rows belonging to the country New Zealand, and there are 955 data rows and 61 columns. Now, from pgmpy.estimators, import HillClimbingSearch. Use HillClimbingSearch to develop the Bayesian network structure. Let HC equal HillClimbingSearch of DF New Zealand. Let's print HC. So it's a function. It creates a function HC. From pgmpy.estimators, import BigScore. BigScore is to estimate the parameters for our binary network, a Bayesian network. Let's set the seed to an arbitrary number, otherwise the BigScore gives us the different values. np.random.seed of 1 to 3. Let big equal BigScore of dfnz. Print big. So it's a function. It's a BigScore function. Let's set the seed to an arbitrary number, np.random.seed of 1 to 3. Let's let best model equal hc.estimate. So hc is the HillClimbingSearch function. Estimate bracket scoring underscore method equal big, and big is the big score function. Print best model. Best model. A Jupyter widget would not be displayed. Let's run this again. Okay. So it's creating the best model. So it has created the DAG, and DAG is directed acyclic graph. Let's import networks has NX. Let G equal NX dot digraph, open and close bracket. Now let's print the best model dot edges, open and close bracket. Let's look at the edges. So there is edge from gender to gender. There is edge from education to AI trust. There is edge from education to Ebony City. There is edge from worry crime to is safer. There is edge from worry crime to worry weather. There is edge from worry crime to worry mental. There is edge from experienced no electric to experienced no water, and so on. G dot add underscore edges underscore from of best model dot edges, open and close bracket, gives us a function, a digraph function. From networks dot drawing dot nx underscore igraph, import graph viz underscore layout. Use pygraph viz to create the layout. Let pose equal graph viz underscore layout of G, and G is the digraph, comma, prog equal neato. Let's print pose. So this is the layout. For each of the nodes. Save the graph G for later use with open bracket dag.gpickle. So this is the name of the file, comma, wb. wb is writing, has f colon pickle.dump of G, and G is the graph, directed acyclic graph, comma f, comma pickle dot highest protocol. So if I look for dag.pickle, if I look for that file, it's over here. Load later by using with open bracket dag.gpickle, rb means read, has f, colon, pickle.load of f. Let's run this. Let's print nodes in G. For node in G dot nodes, open and close bracket, colon, print node. So these are the nodes. Gender, this gender, education, AI trust, worry weather, worry food, experienced water, and so on. For node in G dot nodes, open and close bracket, colon, if without in node, print node. We don't have without in node. Doesn't look like we have without in node. Let's check for IND. Let's check for DIS. Okay, DIS we have DIS gender, DIS skin, experience disaster, DIS disability, plain disaster, dis ethic, dis religion. What about info? Worry info used, info news, info religion, info famous, info services, info weather, info agency, worry info stolen, info internet. What about EXP? We have EXP water, EXP crime, EXP mental, EXP work, EXP weather, EXP disaster, EXP road crash, EXP nomads, EXP no electric, EXP no water, EXP no food, EXP no tell. What about worry? Yes, we have worry in the notes. Worry water, worry food, worry crime, worry weather, worry mental, worry road crash, worry work, worry info used, worry info stolen, and so on. Okay, so assign colors to nodes based on the names. Colors equal empty array. For node in G.nodes, open and close bracket and the colon, if without in node, colors.append, so this is the color, elif underscore ind in node colors.append this color, elif info in node colon colors dot append this color elif this in node colon colors dot append this color elif x in node colon colors dot append this color elif worry in node colon colors dot append this color else colon colors dot append this color, and printing the colors gives us the array of the colors that can be used, that we can use. Let's print POS. So POS is the layout of each of the nodes. Let's print POS.items, open and close bracket. So item gives the node name, comma, the layout, and it gives that in tuple form inside the curved bracket. Offset the labels to avoid overlaps. Let pose labels equal curly braces. As soon as we see curly braces, it's a dictionary. So we are forming the dictionary node colon bracket x comma y minus 10 for node comma x comma y in post.items open and close bracket. So for each of the items in the node and xy tuple in post.items open and close bracket, we want to have in the dictionary node colon space x comma y minus 10. So y is reduced by 10. So it gives us this. Now plotting. So PLT fig comma x equal PLT dot subplots of fig size equal 30 comma 10. This is width 30 and height 10. NX dot draw. So NX is the networks library. NX dot draw underscore networks underscore nodes of G. G is the DAG, the directed acyclic graph, comma pose. Pose is the layout, comma node underscore size equal 300, comma node underscore color equal colors. Colors, remember, is the array of the colors that we set. This one over here. And comma alpha equals 0.8. Okay, I'll show you what alpha equals 0.8 does after. Then x equal x, so this will plot the graph inside the box, and it looks like this. So these are all the nodes. Now if I add alpha equal 0.8, what if I add alpha equal 1? This is how bright the color is. Let's have alpha equal 1. Draw edges with transparency. For UV in G dot edges, G is the DAG, directed acyclic graph. G dot edges gives the two nodes and there is an edge in between. For UV in G dot edges, open and close bracket. So U is the starting point and V is the target. X dot annotate, open bracket. So we'll have apostrophe signs over here, comma, XY equal pose V. So the target and then pose V, set above. Let's see what G dot edges is. Okay, so G dots are the nodes in between, list the pairs of nodes in which has the edge. So for example, this ethnic and this gender. So XY equal pose of this gender and pose of this gender will give us the display for this gender. Which is 275.88 and 803.31. So that's the position of this gender node. And XY text equal pose of U. So pose of U, so U is this ethnic in our example that we are looking at. So this ethnic, pose of this ethnic will give us 245.88, 726.52. So that's the position of this ethnic node. And XY text will be put in that position, comma, let's close the bracket and see what happens. Okay, nothing happens. Let's add one more parameter. Let arrow props equal dictionary of arrow style equal dash, comma, alpha equal 0.5, comma, line width equal 1. So let's just use arrow style equal dash and see what happens. Okay, so we get the edges created in between. Let's add another parameter, say alpha equals 0.5. Let's see what happens. Okay, so the edges become a bit light. Let's put another parameter, line width equal 1. Let's see what happens. So that creates the line width to be 1. Now draw labels. nx.draw underscore networks underscore labels of G, pose, font size, font underscore size equal 15, x equal x. Let's remove font size equal 15 and see what is printed. So x equal x prints this graph labels, put the labels inside this box. And pose gives the layout and G is the graph. Let's see. So that gives the label. So as you can see, by double clicking we can make it bigger, and if we want to make it smaller, we double click again. And we can use this scroll bar to look at the other parts. Okay, let's see if we put fonts underscore size equal 15. Let's see what happens. Okay, that makes the labels a bit bigger. Plain disaster and prepared you, they are separate edge. This religion, gender, ethic, skin, they are all connected. Let's save this figure. plt.savefig of causalnetwork.pdf. So it saves the figure as causalnetwork.pdf, bbox underscore inches equal tight. Let's not put bbox underscore inches equal tight, and let's see what happens. So let's look for causalnetwork.pdf in our directory. Here it is. Okay, so we can see all the nodes and the edges. Experience no water, experience no electric, experience no tail is the separate connected edge. Prepared government, prepared local government, prepared hospital is the separate edge. What if we put the box, boundary box, bbox underscore inches equal tight? Okay, let's see what happens. So there is a box created. So as we can see, we can just reset it and we see box has been created. Okay, what else can we see? We see experience crime, worry crime, And is safer here. Worry info is stolen. Worry mental, they are connected over here. Used internet, education is connected to it. Info weather, info internet, worry info used is connected to it.